Hello everyone, and thank you for tuning in on my presentation about eQual informing early design decisions. I'm Arman, and today I'm going to be presenting on behalf of my colleagues at the University of Southern California and the University of Massachusetts Amherst. eQual is a system that uses simulation to help engineers and architects understand the implications of early design decisions to actually form a system. We evaluated eQual on real-world software systems, and we found out that eQual is highly usable, it is effective, and it scales very well. Now, before jumping into the details of how eQual is designed and how different pieces fit together, there were a few insights that drove this research. The first one is that nowadays there are many points of uncertainties when engineers and architects are dealing with a software system. And what I mean by that is that there are many alternatives that allow engineers and architects to accomplish the same set of functional goals. However, these alternatives directly impact the non-functional attributes of the system, which is currently known as, or commonly known as, the trade-offs that engineers have to think about when designing their systems. Now, another important thing is that there are really no silver bullets when you're thinking about the software system. These software systems are essentially complex, meaning that they have to accomplish all the requirements that is defined for them. Usually that means that they have a large number of states, and for that reason, making decisions is going to be inevitable throughout this process, and that is why engineers need support. So to that end, and before explaining the different parts of eQual, I'm going to go over the terminology that I'll be referring back to throughout this presentation and also in the paper. The first one is a variation point. A variation point is any point in a software system that there exists multiple alternatives to accomplish the same functional requirement. For example, if you're thinking about a distributed system, the number of servers in that distributed system could be a variation point. We could have anywhere from 1 to 4 servers to basically accomplish the computation that we want. That we decide one of these alternatives is going to be the one that we are going to use in our system, for example, 2, then that forms a design decision, meaning that the pair of an alternative and a variation point is going to be a design decision for our system. Now, if we put together all the design decisions that form a system, meaning that all the design decisions that end up accomplishing the functional requirements defined for a system, that is going to be what we call a variant. Now, looking at the architecture of eQual from a high level, we can see that there are multiple pieces that fit together, but step back, we can see that this entire process is actually a 4-step process. It starts from designing, which is creating a model of the system, and its different pieces and how they fit together and how they interact with one another. The second step of this process is going to be what we call preparation. And what preparation is effectively engineers and architects providing a set of answers which bound the problem for eQual. And I'm going to go over the details of what these questions are and how eQual takes advantage of those answers. And then after that, we go to the steps 3 and 4, which happen iteratively until we either exhaust our resources or we arrived at a satisfactory solution. And what we have in these 2 steps is that we select different alternatives for the variation points that we have, forming different variants. We assess the quality of those variants, we compare them with one another, and then we either pick another set of variants or generate another set of variants, assess them, continue this process until we get to a point that we are satisfied with what we have. Now, going back to our design, on the left side, on the architect side, we can see that the process starts from designing and modeling the system. For this part, we rely on Domain Pro. It was this research that was developed in our research group previously, and I'm going to be giving you and showing you some screenshots of what that tool looks like in action. What engineers do here is basically lay out a diagram of how their system is designed and laid out, and how different parts fit together and how they interact with one another. And the second part of that is going to be the preparation interface, and that is where the engineers provide the answers to the questions that eQual asks. the equal system is going to be the controller side, which is after we collected all the information, we have the model, we have the variation points and all the things that are of interest to engineers, and then we use that information to go through the selection phase and generate variance that we want to assess. And the global assessment is actually what I'm going to be talking about in more detail later on, but it effectively compares all the variance that we have generated so far. And you can see the simulation nodes that we have, and that is just what we use for deploying the simulations of each variant in order for us to actually gauge its performance. And we are using a distributed model here because we want to accomplish speed ups using multiple nodes, and it also allows us to create redundancy in the system to better deal with failures as well. Now, I mentioned Domain Pro and the design. So the reason that we use Domain Pro is because of its very simple interface and its ability to provide us with dynamic analysis capabilities, which we really needed in the case of eQual. And dynamic analysis in our case is discrete event simulation platform. Domain Pro conveniently also handles variation points, and it's a model-driven architecture platform. But it is just what we used as the means to prototype eQual. We can completely, it's absolutely fine to swap out Domain Pro and replace it with another model-driven architecture platform that provides these capabilities for us. The approach is not reliant on Domain Pro specifically. To just give you a sense of what a system design looks like in Domain Pro, this is the model example for the test case that we had in the paper. And this is for the Hadoop system. Done, we end up with a set of time series that were generated. And these time series effectively describe all the events and different values and different attributes of the system at each point in time during that simulation. That is what we are going to be relying on later on in the process. So what do we do in the preparation phase? In the preparation phase, we first of all need to define the variation points to eQual. So for each one of them, we ask 3 questions. Basically, after the architects specify what their variation points are, they ask them what is the lower bound, upper bound, and the exploration function that they want to use for that variation point. Something I want to point out here is that these answers could be complete, partial, or architects could say that, I have no idea what the lower bound and upper bound for this specific variation point is. Just rely on, and then try to rely on eQual to explore as many options as possible, and then come back with an answer that helps them decide. An exploration function, you can think of it as a distribution on how we want to sample the interval between the lower bound and the upper bound. It could be a uniform sampling, it could be a normal sampling, so on and so forth. So basically, a little bit of a more advanced guidance for eQual on how to explore this range. The second set of preparation questions is going to be about the non-functional properties of the system that are of interest to the engineer. So here, effectively, they need to define what time series objectives the thing that they're interested in, and whether or not they want to maximize or minimize that specific objective. For example, if you're thinking about throughput, you probably want to maximize the throughput of the system, meaning that this time series is directly related to the overall quality of the system. Whereas if you're thinking about energy consumption, the chances are that we want to minimize the energy consumption of our system. Therefore, it is going to be inversely related to the overall quality of the system. And lastly, they can provide us with what we call an importance coefficient factor, which allows them to maybe stack rank the different non-functional properties against one another. For example, in their case, throughput could be much more important than energy consumption. And that is a way for them to provide the values that could later on be used for a weighted averaging over all the all the non-functional properties of the system. Now that we have the preparation phase done, we are going to be going through what we call the selection. And in our prototype of eQual, we are using a genetic evolutionary-based search-based algorithm to explore the domain of all the variants that we have and all the alternatives that we have. In order to do that, we need to have a seed of variants. So that seed generation is the first step that we need to go through. And then after we have our seed, we go through all the assessment, the global assessment and the local assessment that is happening on each node. We end up with a ranked set of variants. And at that point, the decision is going to be very simple. Now that we have a ranked list of variants, are we done and have we arrived at a solution? And the way that we decide that we have arrived at the solution is that we have either exhausted our resources or the architects find out that the solutions that they have found so far is going to be satisfactory. If not, we will generate a new set of variants. We go through the process iteratively until we arrived at one or a set of answers effectively. Now for seed generation. We realized that one of the ways that we do that is purely randomly picking up some alternatives for the variation points that we have in forming a variant. That is a completely plausible way of doing things, and for so many problems in the space of genetic algorithms, it seems to be working fine. But intuitively, we were thinking about using a strategy that we call edge case. And what that means is that we basically, if you recall the boundaries that we were defining for our variation points, if we pick up the minimum and maximums in those boundaries, or the lower bounds and the upper bounds, and use those values in our variants, intuitively we can think of it as a way to cover more extremums of our system. And that turned out to be actually the case, and I will go over the empirical data comparing these two different seeding strategies later in the presentation. And afterwards, we are going to be doing the assessment. So we are looking at simulation-based analysis here. So what we have is that we have a set of time series objects that we need to compare to one another. Now, some challenges in comparing different time series. The first one is that we don't have a ground truth that the optimal system is going to be behaving in a certain manner. And therefore, we don't really have an optimal time series object that we can compare different variants against. And another challenge is that time series objects tend to get big. For a medium-sized system, we are looking at hundreds of megabytes to gigabytes of data generated for a single variant after a simulation. So comparing thousands and thousands of variants could end up generating hundreds of gigabytes to terabytes of data that need to be analyzed fairly quickly. And another challenge is that if we generate new variants, are we going to have to redo all the assessments that we had done previously, or at the very least, are we going to have to compare the new variant with all the ones that we had previously generated? So for these challenges, we came up with a technique that we call BRTA. BRTA is a bipartite relative time series assessment technique. And the insight that we have for this technique is that we want to either maximize or minimize the time series, depending on the relationship that could be to overall quality that could be direct or inverse. Now, in order to do that, we distribute the analysis among the simulation nodes. Each node computes some metrics locally and then sends back those summaries to the global assessment engine. We use dynamic time looping under the hood and mathematical proofs of how things are done in the paper and in the appendix that is posted online. But at the end of the day, we come up with a way that we can basically infer the distance to global optimal for a time series just using the summaries that are calculated locally. And this allows us to improve the speed of this process significantly. And after the iterations from selection and assessment is done, we end up with a set of solutions and variants that we can compare with one another. And in a lot of cases, we will have Pareto optimal solutions. And in our genetic algorithms, we tend to keep those Pareto optimal solutions because we believe those provide a lot of good information and useful information to the architects of the system. And they can, this is an actual screenshot of the system that a diagram like this, spider chart like this is going to be provided to engineers and architects, and then they can lay down different variants on top of one another and compare them on multiple aspects and dimensions at the same time. We evaluated eQual on 3 different perspectives based on its usability, effectiveness, and scalability. In order to evaluate the usability of eQual, we compared it with just looking from a purely from the point of field entries and a purely mathematical view of that takes us to the formula like how many field entries we're going to be doing in eQual and how many field entries we're going to be you're going to need to complete in GuideArch. And you can see for a system of a relatively large system, and by large I mean having about 10 variation points and maybe 2 alternatives per variation point, not extremely big, but a relatively large system. eQual's footprint is going to be orders of magnitude smaller than GuideArch. The second perspective was the effectiveness of eQual. So we applied that. We applied eQual on the Hadoop model that we had developed before using both eQual and GuideArch, and we saw that our model had similar reliability and utilization compared to GuideArch, but pretty close. But in terms of speed, eQual's variants were 7.5 times faster than GuideArch. So at the very least, we were as good as GuideArch in terms of the quality of the produced outputs. We also wanted to make sure that for systems that have well-known and created performance models, eQual can get very close to global optimal for those systems. To that end, we relied on previous research that had created these performance models for several systems. Here you can see the list of those systems. We applied eQual to these systems, and we found out that, well, first of all, in this column, we can see the default values. And what default means is that just using the default alternatives for the variation points, what is going to be the performance of the system. Random and edge case scenarios, we can get significantly better results than just using the default. So eQual is effective and it can find close to optimal solutions. Here you can see the proximity distribution of the best variants generated by eQual using generation sizes of 50, 100, and 200. And each box plot in this chart comprises 100 executions of eQual's exploration function using the edge cases strategy. And finally, we ran a user study on 15 participants from different companies. On average, they had 11 years of industry experience from companies like Google, Facebook, Samsung, Cloudera, so on. And 2/3 of these participants were using software design models regularly. And for that study, we asked them to design the system in GuideArch and eQual. And we were able to demonstrate that statistically significantly eQual produces higher quality models with less effort and is more user-friendly. Finally, the scalability of the system. We wanted to make sure eQual scales to large and complex system because that is where the benefit is going to be more evident. To do that, we ran scalability analysis based on the number of nodes and model sizes. You see the numbers here. We get pretty close to linear scalability, which is the optimal solution for. In terms of the number of variants that are generated, we can see that we are also very close to linear scalability. And in conclusion, we show that eQual supports evaluation of early design decisions. It allows us to navigate very efficiently through massive design spaces and simultaneously matches or betters the state of the art on different aspects: problem scope, usability, effectiveness, and scalability. With that, I want to thank you all for listening today. If you have any questions, I or any of my colleagues would be happy to field them. Thank you.